to be announced to the class. So that's just a rule. Rules is just like laws in physics. They have to be followed. You cannot change it. Well, it's officially 8:30. Good morning. This gentleman, you're the closest. Could you please help me with a couple of simple demonstrations? So no one would think I cheat. Could you please hold it with your both hands, yeah, like this? That's it. And describe what you feel.
There's a weight.
Try to hold it horizontally. What about now? Well, it's kind of not horizontal anymore. Yeah. All right. What about now? No? Yeah, of course not. I'm going to ask you to help with one more thing. So this is just, again, a demonstration of what torque is. This device has a name, torque feeler, because you can feel it. Because to keep it horizontal, you have to apply force of static friction, but force of static friction has maximum. And by shifting this weight away from the axis, we don't change mass, we don't change force. What do we change? Because we change what? Lever arm. When we increase the lever arm, the torque increases gradually, and force of friction eventually cannot produce torque strong enough to prevent it from rotating. Now, please just rotate one of these and then another and describe what you feel, because I have a question about this situation. So the answer will depend on your description. So please tell people what you feel when you try to rotate these rods. But just tell which is easier, which is harder. So thank you. So this one is harder. So you also should answer the question. So thank you. You can literally feel it, feel the difference. Oops. But what's important, they have the same size and the same mass. So we could think that maybe it is harder to make moving because it's heavier, but it's not. The mass is the same. So it's not about mass, it's about mass distribution. The mass distributed differently. And as we know, when the mass shifted away from the axis of rotation, it increases inertia. So the one which is easier to move, which is the red one, should have the mass closer to the center. You have seen this device already. So it's called the Conic pendulum because the small ball moves in a circular motion, but the string makes a cone. If I entangle it, and I always do. So, same experiment as before. Well, right now, first you have to enter your answers. What do you expect? Case number one, the ball has a larger radius. Case number two, the ball has a shorter radius. And let's call it case number 1. So we have to shorten the radius. That's case number 2. What happened? It's not leveled. What happened is by changing the radius, we're changing the mass distribution of this ball relative to the axis. Come on. Hypnotizing. So there's a second question about this situation. That's why I've been playing with this. Right now you have answered that, of course, with a shorter radius it spins faster. Because, as we just said, the angular momentum must be conserved, and that means this product of inertia times angular velocity must be conserved. But if we decrease the radius, we decrease the inertia, which means we increase the angular velocity. Case 2. Now question about the forces. That's kind of a review. What do you think if we look at the same two situations? First time the ball was spinning slower, making circular motion with a larger radius. Second time, the same ball was in a different equilibrium, spinning faster with a shorter radius. How does it affect, if it does affect, the tension in that string? What do you think? Bless you. And I'm not sure if I need to remind you again. You won't talk. You don't have to whisper. We have friends. Well, I hope. So talk to your friends. And you don't have to wait for me saying, any questions if you want to ask a question. You don't have to wait for me. Well, it's 4 weeks already in this course. When I advise you to talk, you can just talk. And before I will analyze the situation, I want to see the distribution. And the survey says that's the question number 4. By the way, well, on one hand, I hope all possible answers. I hope you will have questions, so we will have some short Q&A session. However, according to the syllabus, I also have to start a new topic today because last exam will not be on Monday, it will be on Friday, so we're losing 1 lecture day. So we can't just waste our time. So the plan is finishing this topic, questions and answers if you have them, and starting the new topic. So let's see once more. For now, all 3 answers have been equally frequent, and so far, well, the answer number 2 seems a little bit winning. If we ask a question about forces, or one force, doesn't really matter. We just said that word, a force. That word forces us to do what? We said it, or even we just thought, force. What do we have to do immediately? Yes, yes, I'm looking at you. Exactly. You have two objects, and you can draw a free body diagram for either. And it's basically your choice. And one choice doesn't give you any information. The second choice gives you information immediately. So, which object do you think should we use as a source for free body diagram to answer this question? The ball or the weight? Why? It spins differently, different speed, different radius. So to analyze the behavior of the ball involves much more thinking. Thinking is something we don't like to do in general. So if we want to relate two situations, if we want to relate two cases, we always have to search for something which remains the same. And in this situation, that same object is the weight. We didn't change it. Well, first time it was a little bit higher than the second time, so case number one. What is the velocity of the weight in the first experiment? Velocity of the weight. You look at me, I'm looking back. So what is the velocity of the weight? What was it? Was it moving up? Was it moving down? When we were just looking at it, the velocity of that weight. What do you think? Was it even moving? This object. That was spinning. What about this one? This guy is spinning, making circular motion. All right, equilibrium is reached, more or less. Come on, all right. The hardest part is, okay, all right, something like that. Is it moving? Is it moving? Is this moving? This. Is this moving? If it's not moving, what is the velocity of this ball? What is the velocity? 0. If velocity is 0 and remains 0, what is the acceleration of this ball? The acceleration, 0. If acceleration is 0, what does it tell us about forces? They have to cancel each other. Nothing new. In this situation, again, the ball is spinning, but the weight is hanging on the string. A different location, of course, but still not moving. So the tension number 1 has to be equal to the weight of this ball. But the tension number 2 also has to be equal to the weight of this ball. So what's the right answer? Is it 1? Wrong. Is it 2? Wrong. The tension is the same. Well, next question. Yes. So I have a spool, kind of string, and I can pull on the string, and the spool might move or not. And the question is, what do you expect to happen if I will be pulling to the right, relative to you, to the right? So, well, of course, we can try different angles, different regimes. For example, if I pull it up, it rolls to the left. If I pull it at a certain angle, it doesn't roll at all, it just slides. And if I pull below that angle, it starts rolling to the right. How do we explain this? Left, right, oops, sliding. First of all, we must say that friction is important, you know? Remember, we said without friction, would be no rolling, would be just sliding. And in this situation, where is my slide? In this situation, it is also about torque. Torque is a base for many, many devices. Wrench, for example. Yeah. It's not just to open and close doors. If you ever use the wrench, you know you don't hold it close to the lips. You hold it close to the end. Why? The force you exert is the same because it's provided by your muscles. But you don't want to use the wrench holding it close to the lips because the lever arm would be so small, your torque wouldn't be enough. That's why you hold it as far away from the lips as possible. And this situation is also about torque, because we talk about torque. Let's more horizontal. Let's make more horizontal. So there is that critical angle, which is easy to find. Here at the bottom, well, first of all, of course, there is force of gravity acting down, and which goes through this point, and there is a normal force. And in general, might be friction, which may point one way or another, but it only touches the bottom point of this wheel. So if I, well, of course, choose my axis of rotation here at the easiest location for this situation, neither gravity nor normal, no friction has any torque because they have no lever arm. So the only force which will provide torque is the force due to the string. And if I aim the force that the line of action of this force goes through this point, even that force will have no torque. In this situation, there could be no rotation at all, because net torque will be equal to 0. Of course, we don't have to, but we could calculate that angle if we knew the radius of a small cylinder and the radius of the wheel. Pure geometry, we don't have to do that. What's important is now we know what's going to happen if we change the angle. Because if I start pulling at a smaller angle, now the torque will be clockwise, and it makes it move in one direction. This was the original question about, so because horizontal clearly is less than that critical angle. That's a critical angle, no rotation, just sliding. And now spinning that direction. Above critical angle, spinning in opposite direction. Without friction, well, situation could have been slightly different, but the answer for this problem is clockwise. Two questions simultaneously. You know that a car might have front wheels moved, spun by the engine, rear wheels, or all four wheels if it's a four-wheel car. In this example, you have a car when the engine, through transmission, makes the front wheel move to propel the car ahead. And without friction, of course, nothing would happen. It would spin as fast as possible, but the car wouldn't even move. So friction is responsible for making it moving ahead. Since we have two types of wheels here, front and rear, well, naturally we have two questions about force of friction acting on front wheels and the force of friction acting on rear wheels. And I just realized I don't have a wheel. I have wheel, but not wheel. Now I have both. I used my will to force myself to get the wheel, and now I have it. Which one is it? It depends. How do you think should I make it move in order to make it a model of a front wheel? Should I move it like this? Or should I move it like this? Like this? See? Those are different ways to make it move. Number one. Number two. Well, the gears make it move like this. It actually tries to move the whole Earth to the left. And according to Newton's third law, the Earth exerts a force from the surface on this wheel. That force is the force of friction, which points opposite to left, which is right. And that is why it's moving. And now another wheel is attached to the frame of the car. I'm a frame of a car now. Without friction, it would be sliding like this. So how should friction point in order to make it spin? That way. So this is the front wheel, and friction points that way. This is the rear wheel, and friction points that way. That's why friction is a very tricky force. So for the front wheel, there is a torque applied through the system of gears from the engine, and well, we could call it applied torque. Without friction, it would just spin clockwise forever without any motion horizontally. Friction makes it move ahead. For the rear wheel, it's attached to the frame, and the force which makes the wheel move ahead is actually acting on the axis of rotation. Without friction, it would just slide to the right, but it spins. How? Clockwise. The only reason for that is friction. These are rare examples when we have to think a little bit in physics to connect things. So those not kind of problems which can be solved by just following step-by-step instructions. But I think it's important to get sometimes a little bit beyond just step-by-step instructions. You get the feeling what science is about. All right, now we are done with this particular topic. We've learned everything. So that's what we're going to learn next, eventually. But before, I'm listening. You know how it works. You have questions, I provide answers. You have no questions, I have to move ahead. So you got let's say 2 minutes to come up with the first question. If in 2 minutes no one asks anything, we have to move on. Yes? Cannot hear you. Please be louder. Yes, if you tell me what is it about. If you think I remember all the problems. Okay, and a child jumps on it, right? Okay, but first you have to tell me what should I draw, because that's always the first step. A picture. So please tell me what should I draw. And I cannot draw merry-go-round. That's too complicated. So please just tell me what should I draw which would represent it. Circle. All right. So, and initially, is it at rest or already spinning? Okay, so initial angular velocity, well, it looks like a disk to me, so you can say disk. If we look from the top, from above. And the child, how, well, child, okay, that I can do. Runs toward, so probably you know velocity, yes? You don't know velocity? After the child jumps on it, right? Oh, okay. So you see, all you should have said, the initial velocity equals number. Okay, numbers don't matter. 1, 2, 3. Dot. Revolutions per, no, 10 revolutions per minute. The mass of this child, let's say 60 kilograms. And the initial speed he or she is running, something. So from rest, so he actually, or she, is pretty close and just jumps. Okay. What do we have to find? Okay. Now you have to ask me a specific question. Very specific question, which would, if answered, help you to solve this problem. You have to ask me a very specific question, which, when answered, would help you to solve this problem. Or anybody else. How to solve this problem is not a specific question. It's an admission that I have no idea what to do. But you know what to do. We've done similar problems, or it's problems in general, so there is always a gap between what we know, what we don't know, and basically all we have to do is just fill it up with steps. And each step represents an answer to a specific question. If you cannot ask a specific question, it means you just given up, don't give much thoughts to it. Because there's always something more than just seen on a surface. So you have to, or anybody else, have to ask me a specific question, very specific, about something very specific, which would help you to bridge this gap. Yes? All right. So, question number 1. Should we use a definition or a law of something? Definitions of what? For example, there's a definition of angular velocity. There's a definition of shape we call disk. Laws, we have learned so many laws. Newton's second law, second Newton's law for rotation, law of conservation of energy, law of conservation of linear momentum, law of conservation of angular momentum. What else? Well, those are the main laws. So, and by the way, they all definitions and laws on the equation sheet, which you should keep in front of your eyes to help to do your search, because that's what you're literally doing, searching through the database. And your search should be based on similarities between the situation you're trying to analyze and the situations which have been analyzed before using those particular laws or definitions. So, and now there is a more specific question. Which law should I use? An even more specific question. Should we use law of conservation of angular momentum? What do you think? Did you use the law of conservation of angular momentum? Okay? So, you have to use the search. It's like a spinning a wheel, but we have to hold the pointer saying, use the law of conservation of angular momentum. What does it say? That's a second question, specific question. It says angular momentum before and after, well, in this situation, collision, has to be the same. How do we calculate angular momentum? That's the next specific question. The answer is provided not by a law. Yeah? The answer is provided by a definition. So we have to do a search for that definition, and the definition says it should be equal to the product of rotational inertia and angular velocity. Well, we should use the subscript, initial, but exactly the same definition we should apply for the final angular momentum. Well, if we made a step, you see how many steps have made already? 1, 2, search 3, law 4, 4, sorry, 4, definition of angular momentum 5. So steps. And after every step, after every single step, we must ask yourself, ourselves, or your friend the same question again and again and again. And that question is, what can I do now? Again, you have to start running the search for a situation similar to yours right here, right now. Because 99% of situations have been covered, analyzed, presented. So we always have something similar done in the past. What can I do now? We do the search in the past. There is a slide which says, now you have to write a definition for I, which is a moment of inertia, which depends on the shape, because merry-go-round looks like a disk. I is equal to 1/2 mass radius squared for the disk. But when there is another person or another small object sitting on the top of it, I, and that's I initial, I final will be equal to the same expression, the same number, the same value for the disk, plus the inertia for that additional object, which has a different mass. And let's keep the same. So the equation says 1/2 mass of the disk, radius of the disk squared, times initial angular velocity should be equal to 1/2 mass of the disk, radius of the disk squared, plus the mass of the person, the distance from the person to the center. If the person jumps on a disk and holds at the rim, the distance is equal to the radius times the final angular velocity squared. Just radius was squared times the final angular velocity, period. I am assuming that in this equation, if you use all the given numbers, there is only one unknown left to you. Yes?
How do you know that for the boy?
Because he's little. Because he's so little, he has no shape. Relative to the size of the merry-go-round, which is huge, and the guy is little. That's it. That's a natural assumption. What is a natural assumption? It's an assumption without making which you cannot solve a problem. That's why you have to make that assumption. Of course, in reality, the person has some shape, and the moment of inertia of the person will be slightly different, but you would have to know much more about that person. If that information is not provided, you have only two choices. Number one, giving up. Number two, make a natural assumption. Yes? If it's a small ball, just the mass. If it's anything small, it could have been small cylinder, small anything, it means it is so small that the size of this object, negligible relative to the size of that big object, disk or something, disk probably, negligible. So mathematical description of this fact is no, like this. So practically zero. No size. All right, that was a good conversation. Next question, yes? It depends.
It's the one about the pilot performing the loop that is weighing at like the load.
Yes? Do we have a specific question? Did you start this problem?
Yes.
Do you have a picture?
Oh, yeah.
Do you have a diagram? How many forces are acting on the pilot when the pilot is at the bottom of this loop? Please name for me those forces. That's not a name.
Force of gravity.
Thank you. If you say name, I know the equation. So force of gravity, number one. What is that specific object which is responsible for the existence of the normal force? Object. An object. What is the name of the specific object which is responsible for the existence of the normal force acting on you? Well, you're not on a plane. Right now, on you. Yeah. I don't think so. I don't think so. I don't think you feel the normal force through feet. I think you feel it through different part of the body. You can lift your feet and still not falling down because something holds you. What? The chair. The chair is that specific object. So if I ask you again, what is that specific object which is exerting a normal force on the pilot? The answer is what? Are you sure? Is he sitting in the chair or just flying? So why so confused? Of course. All right. You said 3. Please name the third force. You can say independence. Every force has a source. For the force of gravity, the source is the Earth. For the normal force, the source is the chair. What is the source for the force you called applied?
The motor of the plane.
So, according to you, the motor touches the air pilot. That would be too dangerous.
Then nothing else.
You're asking?
No.
So how many forces acting on it? 2. All right. Now we have to add one more arrow, which represents acceleration, because it's the force diagram. We need acceleration. How do we point it? Left, right, up, down, into the screen, out of the screen? That's the problem. Now we have found the source of your confusion. You don't know the definition of centripetal acceleration. So you have to read it, memorize it, and use it. Let's say the pilot travels this way. That would have been velocity, because velocity tangent to trajectory. But velocity changes, and that means acceleration is not 0. But the acceleration has a specific direction. So how should I draw an arrow which represents acceleration? Left, right, up, down, into the screen, out of the screen? Help? Anybody? Someone has to say the right word. Where is the center? So if I need to draw an arrow from the bottom toward the center, that direction has a name. What is that name? Up. Every step of the reasoning is important. I'm doing that because it demonstrates the strategy. You skip one step, you're at risk to make a mistake. So you cannot skip steps. You have to follow those steps literally, because it's a law. What do we do now? Diagram is finished. What do we do now? Law. Yep. So normal force minus force of gravity should be equal to m times a. What law did we use? Every force has a source. Every law has a name. Newton's second law. How do we use it now? The problem says calculate the apparent weight. So we have to make a connection between what we are looking for, which is this variable, and something we can find. What can we find? Well, we can find normal force. We can find force of gravity. We can find m times a because it equals mv squared over r. So one of these variables has to be related to this. If we know which, we're done. If we don't know, we only get a partial create. So, apparent weight, what is that? What do we have to calculate? What do we have to find out in order to answer a question about the apparent weight? Anyone? Yes? The acceleration points up. Maybe, I don't know. You're speaking about something else. We still have no bridge built between what we are looking for and what we can calculate. Until we make this statement, everything else is kind of useless. So we have to know an official definition of the apparent weight and use that definition. So, anybody? Jump in. Yes? It is equal to the normal force. It is not the normal force. A normal force is the force acting from a surface or support on an object. And the apparent weight is the force acting from an object on that surface or a scale. That's what apparent weight is. But according to Newton's third law, these two forces must have the same magnitude. So the apparent weight has the same magnitude of the normal force, which means if we need to calculate the apparent weight, we need to calculate the magnitude of the normal force. That's going to be the same number, and the magnitude of the normal force will be equal to, for that location, the sum of two terms, mv squared over r and mg. This, just again, an illustration how many different elements of reasoning have to be used, but those elements do not require thinking. They require knowing those elements and following those elements step by step, like driving when Google Map guides you. Take it left, take right. Unfortunately, so far, there is no Google Map which can guide you through solutions, so it has to be in your mind. And we can repeat the same strategy for the highest point. Now, force of gravity, normal force, and acceleration all point down. So now, technically, the equation with the Newton's second law should look like this, because they all have negative components relative to our standard choice of vertical axis. But now, the normal force will be equal to ma minus mg. Hence, the apparent weight, which has the same magnitude as the normal force, will be equal to this. In particular, if it starts flying slower and slower, eventually, normal force might become equal to 0. That's what we call weightless, because the chair doesn't push on the person anymore. When will it happen? It happens at special critical speed, which can be found from the same equation. We just have to set normal force to be equal to 0. And the critical speed will be equal to, okay, mass cancelled. And if the pilot would start flying even slower at that point, without belt, without roof, he would start falling out. Well, he has, of course, the parachute, so. All right, any questions? Please. There used to be a gentleman in the back, in the yellow shirt. Now I don't see him. No questions? Any questions once? Any questions twice? Any questions? Sold. So, oops. We are starting a new topic, and we're not going to do anything complicated today. We're just going to introduce general language, which we will use to describe the most important motion in the whole universe, simple harmonic motion. Simple harmonic motion is a type of a periodic motion. And a periodic motion is a motion which has a period. For example, oops. These pendula swing back and forth with a certain period. What is a period? Is a time for one complete motion. Oops. This is easier. Swings back and forth. So it always comes back to initial location. Without friction, this motion would last forever. And we can count how many complete motions it makes, like in 10 seconds, and time over number of oscillations. That will be the period. This is another model. Vertical oscillations. This is another model. Horizontal oscillations. As we know from first lecture, all clocks initially have been based on measuring time for one complete oscillation. This is a periodic motion. Well, friction stops it. This is a periodic motion. Of course, friction eventually stops it. But what do they all have in common? For each system, there is a specific state when the object might remain in equilibrium forever. But if we deflect the object from that state, there is immediately a force which wants to move it back. But the object kind of missing that state, and there is a force which again starts moving back to that state, and this state has a name. How do we call an object in a state like this when nothing is moving? Equilibrium. But there are two types of equilibrium. In this situation, this is the equilibrium, the bottom location of this well. But if I deflect, move away from equilibrium, there is a force which tries to move it back. That force wants to restore equilibrium. That is why we call it restoring force. The physical nature of this force may be different. Elastic force here, force of gravity there. But not every possible equilibrium is stable. This is also equilibrium. But now, if I move it away from equilibrium, there is no restoring force. The force actually will move it more and more away from equilibrium. So, all systems which oscillate have a stable equilibrium. And because practically every system in the universe, almost every system in the universe, has a stable equilibrium, that's why this is the most common motion in the whole universe. Well, rotational motion may be almost as common on this one. If there is a stable equilibrium, restoring force always wants to bring the system back in equilibrium. That system undergoes periodic motion, and that's what we want to study. The beauty of this topic is no matter what is the physical nature of the system, we can always imagine that it's only one object attached to one spring. That's it. So if we learn how to describe a motion of an object attached to a spring, we'll learn how to describe all possible systems. I even have a question. The picture below is a photograph of a ball attached to a compressed spring. How do I know it's compressed? Because I see the force pulls to the right, which means and now you have to finish. What does it mean? Where is the stable equilibrium? In this situation, if I pull it down and release, it immediately starts moving up. If it immediately starts moving up, that means restoring force immediately starts moving it back to the equilibrium. So in this situation, if I look at the initial velocity tells me where should be the equilibrium. I could lift the weight and release it. And if I see how it starts moving immediately after being released down, so the equilibrium is below this, but above that point, well, of course it's here. We always can find it. If we let the system sit motionless, we see the equilibrium. And by the way, so we can use this experiment to learn something about springs in general. So this spring now is free of any action. I can pull on it. And when I apply stronger and stronger force, the spring getting longer and longer. But instead of pulling, I can attach a weight, because if I know the weight, 100 grams, I can calculate the force of gravity acting on it. 100 grams, 0.1 times 10, 1 Newton, so I'm adding 1 Newton. And this is now the equilibrium. And this is how much longer the spring has become. What's going to happen if I attach a second one? Of course, it becomes longer again. But if I ask you, did I double the length of the spring? No. No, I didn't. What I changed, what I did double, is how much longer the spring became or has become relative to its free state. So the actual length of the spring does not matter. What matters is the change in the length, or we can say elongation or contraction. And by adding the same weight again and again, I am changing the length by the same value again and again. So I can add one more, and it will become longer by exactly the same amount as before. This is a standard spring, and for every standard spring, the elongation is always directly proportional to the applied force. And in this situation, of course, the equilibrium should be somewhere here, because the restoring force wants to restore the equilibrium. Now, we just ran an experiment, and that experiment tells us that the elongation changes linearly. Yeah? When we don't apply any force, there is no stretch or there is no elongation. And that's what people sometimes get confused about. X versus delta X. Delta X tells us how much longer the spring becomes after we apply force to it. So we apply 1 Newton, it becomes longer by 12 centimeters. We apply an extra Newton, it becomes longer by another 12 centimeters. An extra Newton, another 12 centimeters. So this is the graph which represents how the magnitude of the applied force is related to the elongation or the stretch, if we compress it, compression, if we compress it, of this spring. So how do we write it mathematically? Well, mathematically, we have to use a linear equation. Linear equation in mathematics looks like this: y equals m times x plus b. But in physics, this equation now represents specific variables. This graph relates the magnitude of the applied force, the elongation of the spring. It starts from 0, and the coefficient, which we used to call slope in math, has a name: the spring constant or the force constant, and a standard letter for this coefficient is a k or kappa. I don't know, some people like it. So the unit of this variable spring constant, of course, equals the unit of force over the unit of distance, a Newton over a meter. Has no special name, just a unit, Newton over a meter. That's it. And this is a very important step. We know that the graph for magnitude of a force as a function of magnitude of elongation is a straight line like this. The linear dependency, linear equation relates these variables. However, in reality, in many, many practical situations, we also need to know how to relate actual force and actual coordinate. Actual force points right or left, so it might have positive or negative component. And actual x coordinate also can be positive or negative or 0, because it's up to us how we place the ruler and where we choose the origin. This is a physical equilibrium location. But I can place my ruler like this, like this, like this. If I place my ruler like this, that's 0. So the equilibrium coordinate will be equal to some positive number. Place it like this. The coordinate for the equilibrium will be some negative number. Of course, the most convenient choice, which we should always make if we have that option, is to place the origin at the equilibrium. In that case, equilibrium is 0. And in that case, elongation or contraction of the spring will be equal to that value of the x coordinate we read. And that will be positive x, that will be negative x. Question now, how does force point? Well, we know how. If I move this cart to the right from equilibrium, what will be the direction of the restoring force? Please tell me. Say it. How can we check it? Just let it go and look at it. If we let it go and it starts moving immediately to the left, that means restoring force points to the left. How does the restoring force point now? To the right. So, see, x is positive here. But force points to the left, which makes it negative. X is negative here, but force points to the right. So, if we want to write the relationship between the actual values, we have to write it like this. When x is negative, that makes force positive. When x is positive, that makes force negative. So if we want to plot a graph which relates not the magnitude, but actual value of a force, well, that should be a different type of line like this, because the slope has to be negative. Don't answer this question. This is the standard example of a standard calculation. So let's just do it. We attached a 100-gram weight to a vertical spring, and the spring stretches by 10 centimeters. That's an experiment. We just did it. So this is a free spring. And of course, every spring meant to be ideal, which means has no mass, massless. When we attach a weight to it, it stretches by 10 centimeters. The weight attached to it is equal to mg, which is 0.1 times 10, 1 Newton. This is the force acting on the weight from the Earth. That's why we call it gravity. But it's not moving. There is a force acting on this weight from the spring. Spring force. And of course, it must have the same magnitude. But the force, which we call elastic force, is the force acting in the spring or from the spring on this object. From this object on this spring. So this force, according to Newton's third law, will have exactly the same magnitude, 1 Newton. And if we need to calculate the spring constant, the easiest way is just using magnitudes. We just have to use international system of units for every single variable 1 Newton over, we cannot use centimeters, 0.1 of a meter, 10 newtons over a meter. This is not a very strong spring. It's very easy to be stretched, as you saw. Many professional manufactured springs are much stronger. We have no question like this. And let's see. Well, for this situation, for the ball, which is attached to a spring In the most general case, we should show many forces. So if the spring was compressed, force acting from a spring on the ball moves it to the right. Theoretically, could have been frictional force. And since it's about forces, as we know, it forces us to draw a force diagram relative to x-axis, right here, right now. Force, minus force of friction will be equal to m times a relative to y-axis. There will be no acceleration because acceleration is horizontal, has no vertical component. And of course, we neglect friction. Set it to 0. So, relative to x-axis. This is the equation we can immediately write down. And when we write this equation like this, we make an assumption that the equilibrium is set at the origin, or that the origin is set at the equilibrium. Because that just makes equation easier, this equation. When equilibrium is set at the origin, the elongation delta x of the spring is just equal to x, to the x coordinate of that end of the spring, or that object attached to that end of that spring. Spring constant is a fixed number, depends on the properties of the spring. Mass of the ball is a fixed number. So interestingly, what we have here is a relationship between acceleration and the instantaneous location of an object. This ratio, first of all, is constant. Secondly, always positive. At least for now, we have no knowledge about existence of negative masses. So that's why people name it omega squared, because anything squared is always positive. Physical meaning of this variable will be discussed later. For now, the most important statement is, for simple harmonic motion, like an object attached to a spring moving back and forth, acceleration is always proportional to instantaneous location of an object, always. And in this example, this is linear acceleration and the x-coordinate of an object. For a ball swinging, for the pendulum, we can relate it to angular acceleration and the angle. This is a most important equation for simple harmonic motion. So this is it. And we have it derived for an object attached to a spring. However, the equation itself would work for any system with a stable equilibrium. Only for other systems, this variable, omega squared, would be related to different parameters, maybe to the length of the string or something else. Now, this is an equation. It relates the location with acceleration, and we have to solve it. And it's not very easy to do. because technically acceleration is rate of change in velocity, velocity is rate of change of position. So this is the mathematical equation we need to solve. We cannot do that because that's outside of the algebra. However, we don't have to do that because there is a different approach, physics. We know another periodic motion, circular. So we can relate simple harmonic motion with a circular motion. We just have to use our what? Imagination. So let's say I can make this ball circle with exactly the same period. And let's say I'm looking at it straight down from above. In that case, I wouldn't see the ball spinning. I would just see the ball moving left and right with exactly the same period, something like this. Years and years of practice. But what we know about circular motion is what? Everything. Yes, we do. So now by transition we know everything about simple harmonic motion. All we have to do is just describe how the x coordinate of the ball changes in time. That's it. And how does it change in time? Well, if the ball makes circular motion, I'm not going to ask this question. Just tell me, what do you think is the best equation to describe the circular motion of a ball on a string? If it travels, well, we call it uniform circular motion and travels with constant speed. Would it be the equation number 1? No, because that equation tells us that it's not moving at all. The angle equals 4 radians, and that's it. Would it be the equation number 3? No. This is an equation for motion with constant acceleration, constant angular acceleration. No acceleration means we have to use the equation number 2. That's how the angle changes in time. So, if we know how to describe rotational motion, I'm going to skip this for now. We know how to describe oscillation when we need to calculate the x coordinate, we have to use trigonometry. This is the instantaneous location of the ball, which spins, let's say clockwise, doesn't really matter. This is the x coordinate of this ball. So if you want to calculate this value, it has to be equal to hypotenuse times the sine of the angle. However, if the ball spins, makes uniform circular motion, the equation which describes how the angle changes in time is linear. So now we can combine these equations together. And this is the expression for the x coordinate of a ball. But this equation also should describe the x coordinate of cart traveling with the same period. The only thing is, when we talk about rotational motion, we use this variable letter r to describe the radius of the circle. However, I'm going to go back to this on Tuesday. When we talk about oscillations, we just use different letters. Instead of using R, we use A. Because for oscillations, it doesn't represent the radius. This cart doesn't spin, doesn't rotate. This cart moves back and forth about the position we call equilibrium, but it doesn't go infinitely far away from it. There's the maximum displacement on the left, and there is the maximum displacement on the right. That maximum displacement from equilibrium has a name, amplitude. But mathematically, the amplitude of the displacement of the cart is equal to the radius of that circle. So, finally, we have arrived to an equation which describes a typical simple harmonic motion like this one. The coefficient amplitude tells us the maximum displacement from equilibrium. The coordinate of the cart changes between two amplitudes. And depending on the time and the initial conditions, we can calculate the instantaneous position of this cart using this equation. This is the motion equation for simple harmonic motion. Done. Thank you. I've achieved my goal for today. Don't forget to sign in, please. Yes.
So, that, can you explain to me again why when it's at like this angle, it doesn't move at all? When it's at this angle, it like...
Because the net torque relative to this axis from all forces equals 0, because each torque relative to that axis is 0, because each line for each force goes through this point. So there is no lever arm for neither force. You have to draw a picture to see it. And when it's horizontal, the string now has torque. All other forces still have no torque because still no lever arm, but string now has it. Same. If it's vertical, don't hurt yourself. If it's vertical now, again, only string has torque, so you can put something on the cart so it would hold it. That's it. Just draw a picture. It's about torque. Well, first of all, your picture doesn't show the object. The object has, if you change the situation, your analysis will not be applied to the original problem. So you have to draw the whole spool. The spool is large, but the internal cylinder is smaller, so it makes difference. All details are important. Yes.